Okay, now actually, let's talk about one more goodie, which is the AUC. Remember we saw the AUC for class data, classification data, is the area under the curve. It's a very useful measure of the accuracy of a classifier. Well, it turns out for survival analysis, there's something called the C-index, which gives you a nice analogy to AUC. It's an appealing method for assessing a fitted Cox model on a test set. Or actually, any survival model, but we'll show it here for Cox model. So what do we do? Well, we calculate the estimated risk score for each patient from the Cox model. So just like the publication data, for example, we got coefficients, and for each individual, or in that case, each study, we calculate the estimated risk score, called eta hat of I. I is indexing an observation. And then what's called the C-index, or Harrell, Frank Harrell was the inventor of this, concordance index, computes the proportion of pairs for which essentially the model gets the order of the observations right. So what we're doing here is, this is on a test set. So for each test observation, we compute the predicted risk, and we compute this, think of any two pair of individuals or studies. One had a longer event time than the other. And for those observations, for the model to be correct, we like the risk for the patient who lived longer to have to be lower, right? Because lower risk means you live longer. So this essentially says this is the proportion of pairs that we get in the right order among those whose order we know. Now that's kind of a mouthful, but let me parse this. So among all observations for which yi is greater than yi prime, so the survival time for patient I was greater than that for yi prime, this is the proportion for which the risk for I prime was estimated to be greater than that for I. So that this is correct, right? If the survival is longer, we want the risk of the patient who lived shorter to be larger, times delta I. The delta I is doing here because for some patients, for example, we can't determine in the test set which one survived longer. If, for example, one patient was censored at 9 months, the other patient died at 10 months, we don't know who lived longer, right? Because the one who censored 9 months could have lived past 10 months. So only certain pairs can we actually determine which event occurred first.
So we only count up over those that we can compare.
Right. So again, it's
something you need to digest in your...
Yeah. But it's trying to make use of the censoring observations whenever they have information that we can use, basically. So yeah, so I say it in a nutshell, it's the proportion of pairs for which the model correctly predicts the relative survival time among all pairs for which this can be determined. So again, you sort of have to parse the notation, but that's the flavor of it. And for the publication data, we computed the C-index, and it gave 0.773. It's over a test set, remember. So roughly speaking, it means that the model can predict with 73.3% accuracy which paper of a pair of papers will be published first. So it's got an interpretation very much like the AUC in classification.
It's very popular.
Yeah. Okay, so that's basically it. We're just going to wrap up with some topics which are in the text if you're interested in pursuing them. The censoring we talked about is actually the censoring on the right. But there's other kinds of censoring. There's left and interval censoring, which with the information you get on a patient is not just truncation or censoring on the right, but it can occur at other times during the study. And the models we've seen, actually all the statistics we've talked about, survival curves, log rank tests, Cox's model, can all deal with left and interval censoring and other kinds of censoring. Sometimes the choice of time scale is interesting. Normally one uses calendar time, but if you're looking at a patient's age and how their age affects their survival, you might index time by age and other things. So this is a topic that comes up sometimes. Time-dependent covariates are something which are somewhat unique to this area. In all the examples we've seen, and most examples actually in regression, right, you measure covariates or regressors once for an individual, and they're fixed, they're a static thing. But in some survival studies, you follow patients in time and you measure things like their blood pressure at different time points. So maybe it's a 5-year study and you see them every month. Well, at the beginning you get their blood pressure, but every month you measure their blood pressure. And another very nice feature of the Cox's model is that it can capture the effect of the time-varying covariate which you measure.
Because remember in those risk sets, an observation would be in several risk sets as we're moving along in time. Yeah. And their contribution to the risk set involves their features. Right. Well, if their blood pressure has been increasing, that should be reflected in future times we see them in the risk sets.
And it turns out to be particularly easy in Cox's model because it's sort of a sequential in time construction. You just use the current value of X of the feature at a given risk time. risks, and it's really quite easy. But there's a lot of very nice statistical theory that's also been developed with Cox's model and time-dependent covariates. And then we talk a bit about checking the proportional hazards assumption, which is important. Other things we talk about in the book briefly, we've talked really about Cox's proportional hazards model, which is a linear regression analog for survival data. But some of the other learning methods we talked about in the course, random forest, boosting, and neural networks, have their own ways of dealing with survival data, some of which avoid the proportional hazards assumption. So these are becoming more and more popular and are really currently under development. Finally, I mentioned Terry Thurnell, the author of the Survivor Package. So let's talk about software. Well, the examples in this chapter were all done using Terry's Survival Package as well as the GlimNet package in R. And both these can handle some of the things we just talked about. Well, all the things we've talked about, plus time-dependent covariates, other forms of censoring. And there's other software in other languages, of course. Well, there's other software in R, the models, other kinds of survival models, and also in Python, in the scikit survival collection, and in other places.